Hey guys, how's it going?
What's happening to your life today? You live-
Oh. Yeah, right, it's ready for spring break.
I feel you. What's up?
What's up? Oh, Johnny showed me.
Oh, he did?
Yeah, he did, yeah. His video cut at the perfect time where it's like.
Probably right.
Yeah. Congrats though, that's great.
Exactly a week.
Nice,
Locking in,
nice.
locking in.
What's there?
There's one for good luck.
Yep.
Oh. Oh, you're talking out loud, bro. Racist. Exactly. That's what I'm saying. Hey, hey, everybody's here. Everybody's on talking to me. Yes. Exactly.
I don't feel included in this class, man.
I don't use that.
You know, you don't use that. What's the problem with me being saying words? So we know. Your excuse.
How could you?
So I had to tell him. Yeah, he's out to death. He's not. What now?
Really?
What after? That's a full line. That's a lot. That's a lot. Yeah. They're the most silent classics. Exactly. You're skin. Game bound. Are you good? That is that's fine. That was fine.
Oh.
Don't worry. Yeah.
I don't know something is up.
No, the problem is. So you have a life outside of the video. So this evening. Oh no. We already attended. No, it's about coming. Does it really?
You know, I'll be working at Sam.
I don't even know how to do it. You know, my life is gonna be on this.
Being sampled.
Oh my gosh, as we go see pictures.
I got both of them now, but it's only that number between classes.
No, it's not. Yeah,
You just said you're like,
Yeah. I said I was gonna do it. That's just.
you just said
Okay,
it.
yeah, that's it took forever because he couldn't figure out.
Yeah, it's through gas pipe.
Yeah,
gas.
it's always through gas pipe. Bro, but it's always with. That's why it takes forever. Lucky the guy. Yeah, I talked to it. Yes. Oh, dude, I was really cool. Oh, no. You've been hearing this just how I. Oh, it's something he did together. I mean, what are we? We heard it was like first school. I appreciate you. Saying I appreciate
Wow.
Even though it's long.
I we decided like out here.
You guys didn't start.
That's what I mean. Like,
So, you worked already yet?
that right there, like 45 minutes to finish up. And then we felt it, you know.
Sometimes you're so, you guys had some difficulty?
Yeah, it's about
So the other group was all about. So you guys.
It was all of it. But you might need a little station. Well, that's on a computer. It's actually shut down.
I hope you know this is all being recorded.
Machine speaker for that. In position of it. Same word. I'll wait for you. That's where we. Oh, here. Oh, yeah.
Yeah.
Our answers would be same about that. They would be. You have a picture of this. Yeah. Can I take a photo?
No, I'm actually gonna do that. Choosing my.
Okay, it's 1 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing?
Getting bullied over here.
Wow, that's not my job. All right, so let's go ahead and get started today. So I apologize. It looks like the Wi-Fi is down here, so I actually can't connect my iPad to the internet. So I don't like doing this because it's it's kind of just like lecture slides, but I'm gonna lecture from here. So I'm gonna kind of do my best to kind of highlight it with kind of this pen right here. But these are basically just the lecture notes that I have online. We're gonna go through it like this. But if the Wi-Fi does come back, then I'll switch over to the iPad, but it looks like it's down from now. So if someone in the classroom, if you're kind of keeping an eye on it, if you can just tell me when the Wi-Fi comes back, then just I'll switch to the iPad. Okay, so plan for today is we are going to finish up our lecture notes on internal convection. So I had one example to go over with you. That's the case for a constant surface temperature. So we're going to go through that together. And then we're going to talk just very briefly about turbulence effects as well. Okay, so we'll get that done. And then we're going to move on to the second topic for today, which is free convection. So I'm switching things up a little bit. Traditionally at this part of the semester, then I usually go over heat exchangers. But heat exchangers is a little bit more of an involved topic that I kind of don't want to do it the week right before spring break. So we'll do heat exchangers when we come back from spring break. I think everyone's minds will be kind of in a better place at that point. And so this week we're going to go over something called free convection. All right, so you guys' homework 4 is you guys turned that in on Friday. So homework 5 I just posted today, or yesterday technically, but that's not due until after spring break. And so you have this week to work on it. Spring break, you can work on it there, of course, but you should also be on break. And then I think there's a couple of days when we come back from spring break that you can work on the homework as well. Okay. All right, and so that's all my announcements. Any questions I can answer before we get started for today? Yeah. Oh, let me see. Maybe it's just my devices.
Mine was in trouble right now.
Okay, well, we'll monitor it and see.
Is it not back up?
Let me see. My iPad's not connecting. That's the main one. At least I can connect to the guest Wi-Fi. Let me see if that works.
It's a hot spot.
No, it's okay. Don't use your data.
No, I'll do it. I don't care. Like I have it ready for you too.
Maybe I can hotspot my. Don't use your data. I'll use my data. Yeah, let's do that. Let me hotspot my. Thing is, I just don't know how reliable it's going to be. Let's find it. Is okay. Let's try Zoom now. Yeah, just my signal here is not that great. That's the only thing. Oh, there it is. Apologize, everybody. Get up soon. Duo. Right, we're in. All right, stop sharing here. Let me come here. All right, we're in. Lecture's back on for today. Oops. Okay, so we'll see how stable this is. If someone notices the edgy room come back after, then let me know, because this is not ideal. We're like 5 seconds behind. Okay, here we go. Okay, let's go ahead and get started. Okay, so topic for today is internal convection. Okay, oh, that's not so bad. Okay, so internal convection. So, we were spending most of last week talking about this. This is basically just convection in a confined environment. So usually this is going to be flown a pipe. is, okay. And so what we have here is we have a pipe. Okay, we have flow coming in here, right? And remember, anytime you have fluid flow and you have heat transfer going on, that's going to be convection, okay? Now, the main thing that we're concerned about in these situations is the evolution of the mean temperature. And so, one thing that we talked about last week was that, as, because we have fluid in such a confined space, any kind of heat that gets transferred to the fluid or out of the fluid is going to affect the temperature of the fluid itself, right? That's kind of the main difference between this and external convection. Okay. And so we spent quite a bit of time talking last week about, how do we find expressions for this mean temperature, okay? And so remember we said there were kind of two main scenarios that we can kind of solve for this, right? In reality, this problem is solving for the mean temperature in the fluid is not something that's easy to do just because it's there's a lot of things going on. But there are two kind of approximating kind of situations where we can actually solve for this. And so the first one, what we spent the most time talking about last week was a constant wall flux. Or I guess maybe a better way to say is constant heat flux from the wall. Okay. Right, so I'm not going to go over that one again. That was kind of what we spent majority of the time last time. But basically what we found in the situation was that our mean temperature was simply just, going to be a linear function in X, right? And so you can kind of go back in your notes and kind of see what that expression looks like. So the one that we didn't really spend that much time on was a situation 2, which is constant wall temperature. So I think that's the situation that I think, most people are, I think kind of is a little bit more intuitive. And so in that situation, basically the temperature of your wall, and so what we say here is the wall temperature is TS, okay? That is going to be constant all throughout the length of the pipe, okay? And so last time we did actually solve for the temperature distribution. So we solved for Tm of X. And what we found was that this was a decaying exponential. Okay, so the relationship between these different wall conditions and how that affects the mean temperature, that's one point here. It's kind of a core concept for internal convection, and so that's definitely one thing you want to kind of go back and review about this section. Okay. So what I want to start with today is, we did do an example with constant wall flux. So now I want to do an example where we have a constant wall temperature. Okay. And one question that we got that we discussed last week is, how do you know whether you should assume one condition or the other, right? So I believe last time we did an example with constant wall flux. This is now we're going to do an example where it's a bit more obvious this time where it's a constant wall temperature. Okay. And so as you kind of see more and more of these, and you kind of see the justification for what constitutes a constant wall flux and what constitutes a constant wall temperature, you'll start to kind of get some intuition in terms of which one is more appropriate. Okay, so for this example, let's actually do a biomedical example. So something kind of from my own from my own research. So let's consider blood flow in a large artery in your body. So blood flow is really interesting because, I think a lot of people associate blood flow with, transporting oxygen and nutrients throughout your body, which, yes, that is the main responsibility of the cardiovascular system. But your cardiovascular system is actually also responsible for regulating heat in your body as well. Because if you think about it, you just, a human kind of walking around, you have blood that's kind of constantly flowing through every part of your body. And that blood can basically act as a heat exchanger. And so, a big part of your blood flow and your blood vessels is to regulate heat in your body. Okay, so let's draw that out. So let's say we have a blood flow, a blood artery like this. Okay. Let's say that it has a diameter D. All right. And all around this blood vessel, it's surrounded by tissue. Right. So tissue is kind of a general word that we kind of use in biomechanics. It's used for, I think probably the most obvious case is muscle tissue because you have blood vessels going through all your muscles. But this could also be your internal organs as well. But most of the blood vessels in your body are surrounded by these tissues, right? And these tissues are often at some kind of temperature. So we'll call it TT, or temperature of the tissue. Okay. I wrote it. It's just my Wi-Fi's lagging. T sub C. There it is. Okay. All right. So this would be a situation because your blood vessel here is surrounded by all this tissue that's all at the same temperature. This would be a situation where we can probably assume that the wall temperature is constant in this case. Okay. So right off the bat, we know kind of what assumption that we're going to make in this case. Okay. Okay. All right. So let's look at more of the situations. We have blood coming in. Okay. And the blood is going to be at a different temperature than the tissue. Okay. Which is typically the case. So what we want to do is we want to compute. So let's compute the length of blood vessel that's needed so that the temperature of the blood becomes within 5% of the temperature of the tissue. Okay. All right, because this blood vessel here is going to have a certain length, right? And so by length, I mean length kind of in the flow-wise direction. Okay. And so we want to find out, what is that length that's needed so that, our blood becomes essentially the same temperature as the wall. Okay. Okay. Because what do we know? So in a case of constant wall temperature, we know that our mean temperature is going to look like the following, right? And so if we kind of plot it out, right, based on the solution for the mean temperature that we went over from last time, right? And so if we plot out the temperature difference, right, at first there's going to be a large difference in temperature between the blood and the wall. And then as the blood kind of flows through this vessel, right, it's going to absorb heat from the wall. And then eventually that gap between those two is going to close. And I'm just stalling for time while while my iPad kind of catches up to my drawing here. Come on, I need the visual. Oh my God. Okay. Let me see if I can reconnect to Zoom. Come on. I forgot to tell the Wi-Fi that spring break is next. We can do this next week, but. All right, there we go. Come on. Ah, I apologize, everybody. This is it's kind of rough.
The brain kept popping, so it's hard to get attention right now.
It's crazy how much we rely on like Wi-Fi and stuff nowadays for everything. Try one more time. Come on.
This is only was a 2 part. There's only 2 1. This is, dude, I literally actually no, wow. It's probably like 2, maybe 3. Those cats.
Okay, we'll give it a couple more minutes and then we'll switch back to the static slides. Oh, one. There we go. Okay, we're back for now. Okay, anyway, so because we have a constant surface temperature, right? Eventually what's going to happen is that as the blood flows through the vessel, the fluid temperature is going to match that of the surface temperature, right? And so if we plot it out, and so on the horizontal axis here, we have the length. Okay, and on the vertical axis here, we have temperature. Right. So let's say we have a situation where the tissue temperature is larger than the fluid temperature, right? And so in that situation, we have T sub T like this, okay? So we have a constant surface temperature at the wall. So that's constant throughout the entire length, right? And then if we look at the fluid, right? Initially, there may be kind of a large difference in between the two. So maybe it starts here, right? But eventually, as heat kind of leaves the wall and kind of enters the fluid, then the fluid temperature will start to kind of catch up to the wall temperature like this, okay? So this blue curve here is Tm, which is the mean temperature of the blood. Okay. And so what we want to do is we want to find out how long it's going to take in order for these curves to get kind of, within 5% of each other, right? So we want to find out. So let's say that point is right here, right? So let's say once we kind of reach this point right here, Tm and Tt are within 5% of each other. We want to find out how long that is going to take. Okay. And so to do this, we're going to need our mean temperature equation for constant wall temperature. Okay. Okay. And so in this situation, we have Tm of x is equal to Tm of 0 minus temperature of the wall, which in this case is T sub T, okay? Multiplied by E to the minus pH all over m dot Cp times x plus Ts. Okay, or TT, excuse me. Okay. So for the case, when we have internal convection with a constant wall temperature, this formula here gives us the evolution of mean temperature, okay? And basically, when we want to find out, when Tm is within 5% of Tt, okay? So basically, in order to solve this problem, first thing we need to do is we need to fill in all of the, fill in all the properties here, okay? So that's gonna be step one. So step one is to compute all of these. Right. So the main thing we're going to have to compute here is going to be the convection coefficient H, okay? And then step two, right? Once we've computed all those things, or at least we have expressions for all those things, we're going to use this equation and solve for X. Okay? Because X is going to tell us the length of vessel that's needed to get this within 5%, okay? Actually, let's do that first. So let's actually take this equation and let's manipulate it a little bit so that we can have it be a little bit easier to do. Okay. So let's actually solve for X first, and then we'll actually plug everything in after that. Okay. Okay, so what I'm going to do is I'm going to subtract T sub T from both sides. Okay? And so on the left-hand side, we're going to have Tm of X minus T sub T. Okay. And then we're going to divide this whole thing by the initial condition. So we're going to divide this whole thing by that circled quantity there. So let's divide this by Tm of 0 minus T sub T. Okay. And so all we're left with on the right-hand side is just that exponential terms. On the right-hand side, we have E raised to the minus pH over m dot Cp times X. Okay. Right. So the reason I manipulated it like this is because, we want to solve for the point where the mean temperature of the fluid, bless you, is within 5% of the wall temperature. And so what that basically means is that this quantity on the left-hand side, okay, so when Tm is within 5% of Tt, okay, then that entire quantity on the left-hand side will become basically 5%, right? Because on top there, we're taking the difference between the mean temperature and the surface temperature at some location X. And then in the denominator, we're taking the difference between the mean temperature at the inlet minus the temperature at the wall. And so when Tm of X becomes within 5% of Tt, then this whole quantity becomes 0.05. Okay. And so what we have here is 0.05 is equal to E to the minus pH over m dot Cp times X. Okay. Times X. There we go. Okay. So now we have a much simpler expression here to solve for X, granted that we're able to compute everything in that exponent right there. Okay. Okay. And so we need to have expressions for P. We have expression for H. We have expression for m dot, the mass flow rate, as well as the thermal capacity of the fluid Cp. Okay. Yeah.
So this is calculating, so the rate at which it's like getting to that 5% regular temperature.
Exactly, yeah.
And that's why we wouldn't multiply that 5% by PT just yet.
So we actually, right, so we actually replace this entire expression by that 5%. So if you want to put some numbers on this, and so let's say TT is 100, I think, just to make these clear. Okay. And then let's say that the fluid comes in at 0 degrees Celsius. Okay. And so once this is within 5%, then TM has to be 95 in this case.
Right.
Yeah.
So then we would not, okay. Because we're not equaling it to that 95 degrees Celsius.
Right,
It's
no.
just a range.
Exactly, right. Yeah. So you're taking kind of the ratio between kind of what the current temperature is compared to where it started. Yeah. Okay. So a few of these is, so we have 4 quantities we need to look up here. So P, H, M dot, and CP. Okay. So P is pretty simple. P here, remember, is just the perimeter. Right. And so this can be computed based on the diameter, which we know, right? So perimeter is just equal to pi times d. Okay. So this one's good. Okay. CP, remember CP here, this is a material property of the blood itself. So this one you can just look up in a table. Okay. So this right here is a fluid property. Now, granted, you do need to know the temperature of the fluid itself, which, we are going to assume. Okay. But for now, we can say that, a fluid property, that's something we can look up in a table. That's something that's known as well. So we're good to go on that. Okay. M dot here is what's called remember the mass flow rate of the fluid. Okay. So I'm kind of doing this problem a little bit out of whack because of the Wi-Fi problems. But this is something that's normally going to be given to you as well. Okay. So I will write that down in a second, but we'll say that that's given. Okay. So all that leaves here is just the convection coefficient H. So for this one, we're going to need to use our Nusselt correlations in order to compute its value. Okay. Which, is kind of the whole theme of this entire unit, just in general. Okay. Okay, so let's go ahead and continue with the problem. Let me give you all the other information that I neglected to give you before. Okay. Okay. So I apologize. I should have given you this information at the beginning with the problem, but I'm kind of out of whack of sorts. Okay. Okay, so the given information, we are actually given all the properties of the fluid. So we're given the density. Okay, so density for this fluid is 993 kilograms per meter cubed. Okay. Okay. And that's pretty accurate. So blood is just about as dense as water. Okay. We have its viscosity. So viscosity of of blood is about 695 times 10 to the minus 6. And this is dynamic viscosity. So this is Newton second per meter square. Okay. If you've heard the saying before that blood is thicker than water, that's not quite true. Blood is more viscous than water, but that's probably not as cool to say in like a gangster, thriller. So, but blood and water are about the same density. Okay. Okay, we have a thermal capacity. So thermal capacity, very similar to water as well. 4,178 joules per kilogram Kelvin. Okay. We have the thermal conductivity of the fluid. So we're going to need this for the Nusselt number. This is 0.628 watts per meter Kelvin. And we also know the Prandtl number as well. So the Prandtl number for the blood is 4.62. Okay. Okay, so normally you would look these up in a table, based on the temperature of the fluid, but blood is not something that's tabulated in a table. So, when you have kind of a weird fluid like this, you kind of have to just be given the properties. Okay. All right. Also information about the vessel itself. So we know the diameter. Okay. So the diameter for our large artery in this case will be 3 millimeters. Okay. And we also know the mean velocity. So this is right here. This is going to be the only kind of awkward one. So here, this is the average velocity or the mean velocity in that vessel. Okay, so our average velocity here for our large artery is 130 millimeters per second. Okay, so that was everything that I should have given you at the beginning of the problem. So you can see that CP, which is something that we need for our equation up here, that's given to us. Okay. Well, that was not what I wanted it to be. Okay. CP is not that cool. It's not cool enough to be rainbow. So CP is given to us, right? Diameter also given to us. We can compute the perimeter. Okay. Now the mass flow rate is not directly given to us, but we can compute it based on our information here. Okay, so let's do that first. I can't tell if the Wi-Fi is back up or if my wife paid AT&T a little extra money to get it to work better right now. Okay, let's compute the mass flow rate. So mass flow rate, a little bit review from fluid mechanics. Okay. Mass flow rate is the rate at which mass is kind of traveling through our blood vessel here. So one way that we can compute it is we can take our Q. This is capital Q, where Q here is a volumetric flow rate. Okay. Typically, volumetric flow rate is a volume per second. So in SI units, that's meters cubed per second. Okay. And then what we're going to do is we're going to multiply that by the density rho. Okay. And density, of course, is kilogram per meter cubed. Okay. Okay, so density obviously given to us. We know what density already is. Let's compute the volumetric flow rate. So volumetric flow rate. Okay. One way that you can compute it from from a mean velocity is you can say big Q is equal to mean velocity, multiplied by the cross-sectional area of our pipe. Okay. Where the cross-sectional area of our pipe, we have a circular blood vessel, is going to be pi times the diameter divided by diameter squared over 4. Okay. Okay, so several steps here to plug in, just kind of based on the information that we have, but let's kind of put it all together. So our mass flow rate is equal to times d squared over 4, okay, multiplied by our density. And I don't actually have that plugged in, but you can take this expression and plug it in and get your numbers for this. Okay, because this expression for m dot is everything that we based on everything that we're given. Okay. All right. Any questions on how we got this mass flow right here? Yeah. Thank you. I forgot. There it is. Okay. Any other questions on this here? Okay. All right. So now that we have the mass flow rate, so, this is something that, we can compute. Okay. The other thing that we need to compute here is the convection coefficient. Okay. So let's get on that. Okay. So let's kind of go through our, usual convection problem solving methodology here. But I'm going to speed run it a little bit just so we can kind of, move on to free convection. Okay, so whenever we need the convection coefficient, there's kind of this 5-step process that we need to follow, right? First one. Okay. First one, we need to know what our flow geometry is. So our flow geometry in this case is flow in a pipe. So we have internal convection. Okay. Step two is to compute the fluid properties. Okay. Now, normally for the fluid properties, you would need to consult a calculator of some sorts, and so you need to compute the film temperature. Here, it's already given to us, and so we'll just say that this is given. Okay. Step 3 is we need to compute the Reynolds number. Okay. So the Reynolds number is going to tell us whether our flow is laminar or turbulent. Okay. So for flow in a pipe, and based on the information given to us, our Reynolds number is times the diameter multiplied by the density divided by the dynamic viscosity mu. Okay. So that's going to give us a non-dimensional number. And so we plug everything in for this problem, and what we get is 557. Okay. And so luckily for us, this is less than the critical number. So remember, the critical number for internal flow is 2300. So since this is less than 2300, that means our flow is laminar. Okay. Which is great. Laminar flow is fantastic. Okay. Step 4. So now once we have all this information, we know the geometry. We know our flow is laminar. We know the fluid properties. We can select the correct Nusselt correlation. Okay. Now, this is one of those interesting cases, because remember, in internal flow, if you have laminar flow, our Nusselt number is just a constant, right? And so for the case of constant surface temperature, our Nusselt number is 3.66. Okay. So this is our Nusselt number for internal flow with constant surface temperature. Okay. That's great. So there's nothing really for us to plug in. Okay. I should say this is laminar internal flow. That's kind of an important part. Sorry about that. Right. So remember, this expression for constant Nusselt number is only viable for laminar flow. Okay. Okay. So now that we know the Nusselt number, we can now use this to compute the convection coefficient. Okay. So that's step 5. Okay. Because we know that H is equal to our Nusselt number multiplied by the thermal conductivity of the fluid divided by the diameter. Okay. So let's plug everything in here. So we have, we know our thermal conductivity that was given to us. We know the diameter. We just found out what the Nusselt number is. And so in this case, our H is 703.36 watts per meter squared Kelvin. Okay. So I know that was kind of really fast here, but this kind of 5-step process, make sure you kind of know it because it's important for this section here. Okay. Any questions on this here? Okay, good. Okay, so now that we have H, we have everything else that we need. We have the mass flow rate, we have the perimeter, we have everything. Okay, we can then plug all this in and solve for X. Right, and so we have X is equal to minus natural logarithm of 0.05 multiplied by rho times the diameter times CP divided by 4 times the convection coefficient H. Okay, so there was a little bit of simplification here, but we kind of need to kind of move on here. Okay. But after you kind of plug everything in, you plug in for the diameter, you plug in for the mass flow rate. This is kind of what you get. And what we get from this expression is 8.7 meters. Okay. Which sounds like a lot, right? Because, an average person is not 8.7 meters long. But, if you think about it, a lot of your blood vessels are kind of coiled up within your body a lot. So it's, if you think about kind of, taking a rubber band or taking a string and kind of wrapping it around your finger, you can do that, maybe several hundreds of times. And so you can have a lot of string kind of compact into a small area. And so your blood vessels are kind of the same way. I think someone measured it once. Like if you took every single one of your blood vessels inside a person's body and kind of laid them end to end, I think you could actually stretch across, several hundreds of miles. So that's just how many blood vessels are in a person's body. How someone found that out, I don't know. I'm not going to ask or find out, but that's kind of the estimate for that. Okay. Yeah. That is rho density. Yeah. Mm-hmm. Right. So 8.7 meters sounds long, but if you think of it going back and forth, it's a lot. Yeah, so some things that you don't associate to be very long, like a tuba, when you stretch it out, can be a lot. All right, any questions on this example here? Okay, one final thing before we move on to free convection. Let's talk about turbulence, because everything that we've been talking about so far with internal convection has been on laminar flow. So it is possible to get turbulence in internal flow. I believe, one of our previous examples had that as well. Okay. The unfortunate thing is that turbulence makes things extremely difficult to analyze. And so, without going into some really high level graduate stuff, that's kind of the most that we can say. So we can say turbulence makes things just really difficult. Okay. So in these situations, when you do have turbulence in internal flow, we actually kind of default back to our old flow over flat plate turbulence, right? Because it's not nearly the same thing. So you have internal flow is very different. But with turbulence, it's kind of all bets are off with turbulence in a lot of ways. And so in this situation, your Nusselt correlation And this is neutral correlation based on the diameter, okay, is going to be 0.03 or 0.023 times the Reynolds number based on the diameter raised to the 4/5 power multiplied by Prandtl number raised to the n, okay? So if you look at this correlation, this is very much almost exactly the same as our turbulent neutral correlation for flow over flat plate, right? Even right down to the coefficients, okay? Now, the only difference here is in the value of n, okay? So n here has two possible values. So n here is 0.4 if Ts is greater than Tm, okay? And so that's a situation where your fluid is being heated by the wall, okay? The other situation is that n is equal to 0.3 if Ts is less than Tm, okay? And so that's a situation where the wall is being heated by the fluid, okay? So that's kind of the only difference in between that, okay? So basically you would use this correlation when the Reynolds number based on the diameter, okay? And that's kind of the key thing here with internal flow too. So, don't use the length of the pipe. For the Nusselt number, for the Reynolds number, you want to use the diameter in these calculations. Okay? So you're going to use this correlation when the Reynolds number is greater than 2300. Okay? And that's kind of all I'll say with turbulence, because, we could probably go on for, ages talking more about turbulence and pipe flow. But I'll leave it there. Okay. All right, any questions on this before we move on to free convection? Okay, all right, so that's everything with internal flow. So I apologize, that did take longer than I thought because of the technical difficulties. So I think free convection is going to get shortchanged a little bit, but that's okay. Free convection, kind of a chill topic in a lot of ways. Okay, so let's go ahead and move on to the next set of lecture notes, which again is called free convection. Okay. Free convection is really cool. It's something that's like, wow, I didn't expect that to happen. But at the same time, it's also not super impactful in a lot of ways as well. Right? And you'll kind of figure out what I mean by that in a second. Okay. Okay. So let me start with this statement. So up until this point, we've been talking a lot about convection throughout this whole semester, actually. And kind of the assumption is that there's some kind of force that's driving the fluid flow. And so another way that we can say that is that up until this point, all of our convection has been what's called force convection. And all that basically means is that there's some kind of external force that is driving our fluid to flow from point A to point B. Okay. And so we've always just kind of assumed that the fluid has some kind of velocity. How it got that velocity was, usually not of concern to us, but there's usually some kind of pressure difference, or there's some kind of atmospheric forces that's driving our fluid. Okay. And so I've kind of been telling you up until this point that if there's no motion, or if your fluid is completely still, then you don't have convection at all. But let's revisit that statement. So let's say, is it possible to have convection heat transfer when there's no external forcing, or there's nothing that's forcing the fluid to move? So is it possible to get convection? So, you do need motion. So kind of a requirement for convection is that there has to be some kind of motion in the fluid. Otherwise, you just have pure conduction. But if there's nothing driving the flow, is it possible to get fluid flow in that case? And of course, the answer is yes, right? So I'm asking this question very rhetorically. But how can that be? So let me kind of draw a picture for you to kind of show you what that looks like. Okay. So let's say we have a situation here. So I'm gonna have two plates, okay, and we're gonna make a sandwich out of the plates. So we're gonna have one plate on top and another plate on the bottom. Okay. And so, just for the sake of argument, we're gonna say the plate on the bottom here is hot. Okay. So let's say we've provided some kind of heating element to this plate right here so that it heats up. Okay. And the top plate here is going to be cold. Okay. So we have kind of an innate temperature difference in our fluid here. Okay. And then in between, we have some kind of fluid. So, it doesn't really matter what kind of fluid, we'll say is water. Okay. So what's going to happen in this situation? So, we know just based on our intuition here, and assuming the water is just some kind of ambient temperature, that the water in contact with the hot plate is going to get heated, right? And so you're going to have heat transfer from the hot plate into the fluid. Okay? And so what's going to happen is that the fluid that's closer to the hot plate is going to warm up or heat. Okay. Whereas at the top plate, right, because that top plate is cold, that plate is going to absorb heat. Okay. Right. And all of this is happening just by pure conduction, right? Because we're assuming that our water here has no motion to it. I don't know why I wrote that one in all caps. But in other words, we have hot fluid at the bottom and cool fluid up top. Okay. All right. So as the water kind of changes temperatures, right? Another thing that we've learned, over the past few weeks is that the properties or the material properties of a fluid depend very strongly on its temperature. Okay. So as the fluid kind of heats up near the bottom, that's going to change some of its properties. Same thing at the top, right? The most important property that we're going to talk about is its density. Okay. So density, we have the symbol rho, okay? And what do we know about density and fluids and temperature, right? Generally, as a fluid heats up, its density goes down. Okay. And of course, the opposite is true as well. So as a fluid cools down, its density goes up. Okay. And so all of a sudden, you have less dense fluid on the bottom and more dense fluid on top, right? What's the natural thing that's going to happen? Because we do have gravity here. Okay? So we're going to assume gravity kind of goes in the downwards direction. Okay. Right. So very similar to how a hot air balloon works, right? The fluid from the bottom is going to start to rise up. Okay. And then the fluid from the top is going to start to fall down. Okay. And then as the fluids kind of move up, they're going to get more dense as they get to the cold plate. So that's going to cause them to go down. And then as the fluid comes down, it's going to heat up and become less dense and then go up, right? All of a sudden, our situation here where we have no external forces, right? All of a sudden we have some motion. So without any kind of pressure difference, any kind of fan or anything like that, we have relative motion in the fluid that's driven purely by density differences, okay? So this kind of motion where, it's driven purely by differences in density as the fluid heats and cools, this is called free convection. Right, and so what we say, the exact forces that's kind of driving this flow are buoyancy forces, right? So kind of if you remember that from hydrostatics. So buoyancy driven fluid flow is called free convection in a thermal setting. Okay, so that's kind of what this whole unit is about. Now, is this significant? So if you compare free convection to our typical kind of forced convection, free convection a lot of times is pretty negligible. A lot of times, you can't get that extreme differences in the density to really kind of drive, convection heat transfer, okay? So I think, this is kind of a good topic to kind of go over kind of right before spring break, just because, we're all kind of looking forward to spring break. Heat exchangers is the more important topic. But, there are situations where free convection can actually provide a big difference. And that's usually in cases where you have a very large temperature difference between your solid and the fluid. So in most situations, unless the problem explicitly tells you to consider free convection, a lot of times you can ignore it. But for the times where you can't ignore it, it is, it's one of those really, really cool things. All right, any questions on this so far? Okay. All right, so that's kind of the introduction to free convection. And so the geometry that we're going to focus on for this section, just to kind of make things simple, is a vertical flat plate. Okay. And so you have a flat plate. So at this time it's kind of standing up. Okay. All right. And so let's say we have a situation where the flat plate is at some temperature Ts. Okay. And we'll say the fluid outside or kind of far away has some temperature T infinity. Okay. So this T infinity is the ambient fluid temperature. Okay. And so if Ts is greater than T infinity, okay, this is going to cause the fluid near the plate to heat up and get less dense. Okay. And if they become less dense, that means they're going to rise, right? So you're going to have an upward fluid flow near the plate. Okay. And so what's going to happen in that situation is that you have a boundary layer that's going to form here. Okay. And then inside the boundary layer, you have a fluid velocity like this. Okay. Right, so this kind of parabola that I drew here is kind of the upward motion of the fluid due to the density differences. Okay, so that's the situation that we're going to kind of focus on for now. Okay. And so just like we've typically done, in the last 2 weeks, the main thing that we're interested in solving for in these situations is the convection coefficient. Okay. And so we are once again going to, compute Nusselt numbers, and from the Nusselt number, based on kind of the properties of the fluid, we're going to compute the convection coefficient. So same as we've been doing for the last few weeks. Okay. It's just that, because the nature of this flow is different, because it's density driven as opposed to, either pressure driven or things like that. It's going to change our process a little bit, but the same general process is going to occur. Okay. Okay. Any questions on this so far, free convection? Okay, so I think, we have just enough time to kind of introduce the process today. And then, we'll kind of really get into it and do some examples on Thursday. Okay. So how are we going to compute the convection coefficient in these cases? Because, because the driving force in these situations is buoyancy. Oh, question, yes.
So you have like a scenario like boiling like a pot of water. I know there's food convection soup pot, but you look at it from just like the fluid and the pot itself, like the water wouldn't be moving initially, right?
Yep.
But considered free convection to a certain point, well, it's like obviously boiling and moving a lot.
Yeah, of course, there's variations to this. So based on, the temperature difference between the fluid and the solid, you're going to have more flow, if there's a larger temperature difference. And so, there's a difference between a pot that's just starting to boil versus one that's like really boiling and boiling like that. So yeah, there are differences. And I think it gets really interesting and really big differences when you have phase change. And so with boiling, particularly, you have bubble formation. So that's going to change things a lot too. So we're not going to get into that here, because that makes things actually really complicated if you have bubbles. Yeah, but what you're going to see is that, what we compute, it does actually depend on that temperature difference. Yeah. Okay, so how are we going to compute our convection coefficients in this case? Okay, so just like before, we are going to compute the Nusselt number. Okay. And in the past, we know that our Nusselt number is some function of the Reynolds number and the Prandtl number. Okay. So those are usually the two main kind of non-dimensional numbers we have to compute in order to compute the Nusselt number. Okay. But the problem with this is that, the Reynolds number is really a number that's based on kind of forced convection, right? So in order to compute Reynolds number, right, we need to know the fluid velocity. And with free convection, we don't know kind of what the velocity is. We usually just know what the temperature difference is. Okay? So the Reynolds number is only really appropriate when you have forced convection. right? We've kind of taken it for granted up until this point, just because the fluid velocity was pretty much always given to you, except for that one example. But you know, we've usually almost never had an issue computing the Reynolds number. Okay, with free convection, we are going to have an issue computing the Reynolds number, just because there's just no way to do it. Okay, so we need an alternative for the Reynolds number that we're going to use in free convection. Okay. Right, so it's going to change our coefficients a little bit. It's going to change our Nusselt number, but luckily there actually is an alternative to the Reynolds number for this exact situation. It's just credited to a different scientist, and so the number that we're going to use instead is called the Grashof number. So the Grashof number, GR, so this stands for Grashof number. I think it was German. Not sure. Okay. So the Grashof number, well, let's talk about what it represents first. So the Grashof number represents a ratio of buoyancy forces over viscous forces. Okay. If you remember, you know, when we talked about the Reynolds number was a ratio between inertial forces and viscous forces. Okay. Right, so the Grashof number is going to basically play the same role for us in free convection, and so the expression for the Grashof number. So up top, we need some kind of expression for the buoyancy forces. Okay. Is this the same Grashof as 4-bar linkages? I'm not sure. It might be. They're very different. They're very different fields of study. But then you know you have some people like Newton that and Euler that are in lots of different things. So it might be the same person. I'm not sure. So the Grashof number is G, which is gravity, times beta, multiplied by T of the surface minus T infinity, multiplied by the length of our plate cubed, okay, or some kind of characteristic length. And then this is all divided by the viscosity squared. Okay. Okay, so everything in this expression here, we've seen before. So, well, gravity we haven't seen in a while, but G here stands for gravity. Okay. So in SI units, that's simple 9.8 meters per second squared. Okay. The only other person that we don't know in here is the beta. Okay. So this beta here is called the volumetric thermal expansion coefficient. Okay. And we will talk about how to compute that later. But typically you compute this as a function of the film temperature. Basically, this is a measure of how much the fluid is going to expand based on its heating, right? So as a fluid heats up, we know its density is going to kind of go down, but different fluids have different rates in terms of how their density changes with temperature. And so that coefficient there kind of expresses that fact. Okay. So now that we have this Grashof number, now we can use it to compute the Nusselt numbers. Okay. So now instead of relying both on the Reynolds number and the Prandtl number, right? Now we can compute Nusselt number from the Grashof number and the Prandtl number. Okay. And so this will be the last thing I kind of leave you with today, is that the Nusselt number in free convection based on the length scale of the plate is equal to C, which is some coefficient, multiplied by the product of the Grashof number and the Prandtl number raised to the n power. Okay. So that's kind of our generic expression, right? And so, it turns out that the relationship between Nusselt number and Grashof number has the same kind of exponent as the Prandtl number. Okay. And so this kind of splits into two cases here. Okay. And so in the case when we have laminar flow, right, our Nusselt number based on the length of the plate is equal to 0.59 multiplied by the product of Grashof number and Prandtl number raised to the 1/4 power. And then for turbulent flow, okay, we have the following relationship. And so in this case, Nusselt number based on the length of the plate is equal to 0.1 multiplied by the product of Grashof number and Prandtl number raised to the 1/3 power. Okay. And when does turbulence occur? This will be the last thing. Okay. So turbulence occurs when the product of the Grashof number and the Prandtl number, okay, by itself is greater than 10 to the 9th power. So actually very, very large. But what you're going to see is that our numbers here are going to be quite large. Okay. Okay. All right. So that's all the time we have for today. So when we come back on Thursday, we'll do an example with this so you can kind of see free convection in action. Right. So I apologize today for the technical difficulties. Hopefully the Wi-Fi is fixed by Thursday. And then we'll go from there. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys all on Thursday. Yeah.
This is the Grashof formula. T something minus T.
Oh, that's the temperature of the surface.
Yes.
Oh. Sorry about that. Let me see. Oh, it was about Grashof and yeah.
So, like I might look into it already, but going back to that question, that example.
Yeah.
I was wondering if there's any parallels between this example and your biomechanics.
Actually, so not that much. I do teach another biomechanics class based purely on blood flow. So that's 442. Got it. There's a lot more parallels than that. Got it. Yeah. Okay, cool.
So no parallels between this and 441.
Not yet.
Okay, not yet.
Probably not.
Gotcha.
Yeah.
Okay, gotcha.
How are you? Yeah.
It's called organizing.
You guys have a good one.
No, we're editing.